session is called Life of a Serverless Event. Really the intent here is to just a little bit lift the cover on what goes on underneath in the serverless infrastructure that we have in cloud, what the building blocks that we've built on to provide the serverless products that you can use. So before we get started, I just wanted to level set on an assumption here. And the assumption is that we all agree in principle that serverless generally is the place that we want to be. You're not managing infrastructure, you're not dealing with load spikes, we'll deal with that for you. You're not spending time managing things that don't add value to your business. You've elevated yourself to a higher plane of existence. However, there are some problems. Definitionally, we gave you a black box. And we said, you don't have to worry about all this magic, we'll do it for you. But that leads to some issues in terms of visibility and transparency. You might see some latency increase, and how do you reason about what that might be? Maybe your build times suddenly got longer. Why is that? And then you might see different behavior in one environment versus another, or you're hitting some weird quota limit, and how do you reason about it? So the theory is great, you don't have to worry about anything. The reality is you still have to worry about these things. So the purpose of this session is to just give you insight into what's going on underneath there so that you can reason about these with more intelligence. And obviously you would have logging and monitoring and all sorts of things in place, but as engineers I think it's useful to know what are the mechanics going on under here. So we'll cover these 4 topics. First of all, what's the definition of serverless compute on cloud platform? Secondly, what happens when you deploy? What steps do we actually take when you write that command line, gcloud functions deploy? What happens when we receive an event or a request? How does that travel through the system and what happens? And then we'll close with some best practices. What do you do with this information once we've revealed it to you? Serverless compute on cloud platform covers 2 products mainly, Cloud Functions and App Engine. I'll be referring to these throughout the talk as an app and a function. You deploy an app with App Engine, you deploy a function with Cloud Functions. And there's just a distinction that I've made there. An app is something that reacts to requests, a function is something that reacts to events. You know, there's many distinctions you can make. That's just illustrative. Okay, how do we build a serverless compute platform? Now, if you wanted to go and build your own serverless compute platform, I'm going to tell you how to do it now, so take notes. And if you want to go out and start building your own, then this is how you do it. Step 1, you need a global footprint of data centers. It's pretty simple. There are actually servers underneath serverless. As you would know, Google has a global distribution of machines in data centers, so it all starts there. The next layer that we have is something that we've talked publicly about. It's this thing called Borg. And what it is a shared compute infrastructure that runs pretty much every service in Google, everything from Google Maps to YouTube to search and also cloud. And its premise is that Google engineers, in fact, operate serverlessly and have done for a very, very long time. They don't reason about physical infrastructure. They just create tasks in Borg, and those tasks go and execute. The caveat is that it only runs trusted code. It runs code that is cryptographically verifiable as Google code. And your code, I hate to say it, is untrusted. So how do we run untrusted code? Earlier in the year at KubeCon, we talked about the open sourcing of a project we call gvisor. And gvisor is a unique technology that we've created that is a sandboxing technology. It allows us to isolate processes on a shared compute infrastructure from a security standpoint. So process A has no mechanism by which it can interfere with process B. This allows us to run untrusted code on an otherwise trusted infrastructure. So above the data center, above Borg, above these secured processes, we have a serving, routing, and scheduling layer. The serving is the data plane that receives requests. It's responsible for routing. It does things like if a zone in a data center is unavailable, it will automatically move an application to a zone that is available for that sort of failover guarantee. And the scheduling part of it is the thing that decides whether a new instance of your application needs to be created, whether there's an old instance that can be evicted, and makes those decisions to auto-scale you up and down. And above all of that is the Google front end. The Google front ends sit at the edge. They sit in front of every single Google service. Once the request hits the Google front end, from that moment onwards, it's on the Google network. It's on the Google operated network from the Google front end. And it has some other characteristics, like it does SSL termination, it does some amount of denial of service protection, and that's the main entry point at the edge. Okay, so does all of these layers, does it all work? We send this many requests per year, 127 trillion, that's a meaningless number, but really it's about 4 million QPS on this infrastructure, this serverless infrastructure across both Cloud Functions and App Engine. That's a pretty big number. Okay, let's get to the good stuff. I'm going to talk about the life cycle. What happens when you deploy? When you execute that CLI command, what's actually happening? And then once your application is serving traffic, how do we route the request to you, and what's going on? How are we scaling up and down, and what are some of the side effects of the implementation we have? Okay, first of all, deployment. You enter this command into your CLI, or you use the UI, and the first thing that happens is build. We're going to build your, concretely in the case of App Engine and Cloud Functions, we're going to build a container image. And the latency there is going to be a function primarily of the file size and network speed to get the data up to us. Then we're going to actually crunch that together into an image, and most of the time spent there is resolving dependencies. Particularly in Cloud Functions, we have this ability to resolve the dependencies for you. If there's any Node.js developers in the audience, you'll recognize this as a package.json file that you will upload along with your source code that declares a set of dependencies in Python requirements.txt. We will go and resolve those for you and bake it into an image, so you don't need to upload all of your dependencies in one go. Once it's built, we create or update that instance on the infrastructure. And the latency there is a function of two things. One is cold starts, which I'm going to talk a lot about today, and the other is a rolling deploy, which doesn't seem like a latency impacting thing, but the idea here is that you already have a version of your application running, you want to make a change to it. That version is already serving traffic. You don't want to kill that traffic. You want to gradually roll that out. So the time between when you made the change, when you updated the function, and it becoming available across the fleet is not instant. It's never atomic. And so there's an amount of time that that's going to take that could be perceived as sort of deploy time. Just reiterating, at the point we build this dependency resolution, we have some caching mechanisms there. If you depend on a particular version of a particular module or library, and we can reliably identify that we've seen that before, we'll pull it from cache. And then the rolling deploy, again, it's not atomic. It happens over the course of time, depending on how much traffic you have. If you have a lot of traffic and there's a lot of instances of the old version, then it will take longer for the rollout to complete. If dependencies change, a side effect of the caching, obviously, if dependencies change, then the build time might take longer because they're not cached. Okay, what happens when we serve? So we have from the diagram before, serving and scheduling. These red boxes represent the instances of your application. A request comes in. If we don't have an instance that is available to serve a request, then we'll create a new one. will scale up. And this implies a cold start. I might be preaching to the converted here in the sense of what a cold start is, but it warrants some detail. Okay, I'm going to take a quick detour. I put this slide in to remind me that it's a detour. And I will talk about three things really quickly. This is a little bit complicated, but I'll do my best. Concurrency and billing. Products like Cloud Functions. One of the advantages of this is you're not paying when you're not using it. And even more fine-grained than that, you're only paying while your code is executing. Now, you can imagine that, let's say I have a function and I've said, I would like 512 megabytes of RAM, please. And my function executes for 10 seconds. And so I'm paying for 10 seconds of wall clock time multiplied by the amount of memory and the amount of CPU that I've been granted for that period of time. If I was to put another request at the same time in there, the billing gets a little bit complicated. Am I being charged for both requests at 512 megabyte? Am I sharing it somehow? What if they're not at the same time? One starts now, one starts halfway through. It starts to get very, very complicated. The simplicity of the billing model means that we're constrained to a single request per instance. So a function is billed per request independent of the instance. It's not your problem whether there's 1,000 instances or one instance to serve that request. We might be doing a really poor job of our scheduling and have 1,000 instances sitting around costing us money, but it's not costing you anything. An app, conversely, you pay for the life cycle of the instance independent of the request. This is a fundamental difference in the model, and the reason I have the slide here is just to make this clear. An app will deal with many concurrent requests because it doesn't affect the billing at all. The only thing that affects the billing is the life cycle of that instance, and that instance will stay alive as long as it's serving requests. So this has an implication to things like cold start. In this chart along the bottom, I have the frequency of cold starts. How often do they occur? And on the y-axis upwards, I have the duration. How long does each cold start take? These two happy faces are places that we would be okay with. One where a cold start happens a lot, but it doesn't take very long. And the other where it might take a long time to start, but it doesn't happen very frequently. A virtual machine is very much on the top left. And we hope a cloud function is very much on the bottom right. It is necessarily, definitionally, going to have more cold starts because it deals with a single concurrent request and we're scaling up and down. We don't want a lot of machines sitting around costing us money. That means we have to charge you more. So we're going to try to be reactive very quickly to these spikes and troughs in traffic. But it means that you want the cold start time to be low. Typically, this manifests in a difference between the primitive. An app will typically cold start less frequently, and you can imagine this scenario. An app, let's say, it takes 10 concurrent requests before its resources are exhausted and we need another instance of it. If you only have 10 requests, 10 QPS, let's say, we only need one instance, so that is starting very infrequently. You definitely don't want to be this person. Very frequent cold starts that take a long time. That's the worst place to be. This would be the awesome place to be, but it's a bit mythical. Very, very infrequent cold starts that don't take very much time at all. I mean, it does happen. You might have a function that has a very quick cold start that's called once a day, and that's great. But if you're building a large application, the likelihood of this happening is pretty low. But as long as you're in one of those green spots, you're probably okay. Okay, so this makes the distinction, the choice you're making between the primitive pretty important. If you're building something that is multi-purpose, so it has many endpoints, like imagine a RESTful API that has many endpoints. Maybe there's some shared state. Maybe you have a connection pool or some bit of memory that you're sharing between requests. And you want to deal with many concurrent requests at once because of this shared state, then you would err on the side of an app. If, however, your compute unit is single purpose, it really just has one job, there's no shared state, all the state is stored outside, and you're okay with a single request at a time. And by the way, single request at a time is often much simpler you have to deal with far fewer race conditions when you only have a single request in scope at any one moment. Then a function is where you would tend to find yourself. Okay, there's the end of my detour. Okay. Again, on this idea of app versus function, in the app case, and this chart represents CPU time, so M cycles or clock cycles, and then along the x-axis, the wall time, the time back in the real world. Imagine you have two requests sequentially. One request starts and finishes, second request starts and finishes, and some amount of time in between. The blue line here represents CPU usage, effectively. So in an app, let's say the first request uses a little bit of CPU, the second request uses a lot. And there's this time in the middle where the CPU is being used. This is important because, as I said before, the billing model says I'm paying for the life cycle of an instance. So I should be able to do anything I like during that life cycle. And this is true in the case of CPU usage. If I'm only paying while my request is in scope, as in the function case, then there's not going to be any CPU activity in between those requests because there's no billing model that accommodates for it. So request number one, the billing starts on the left, and then when that request ends, we stop charging you. If we allowed your CPU usage in that gap, free Bitcoins for everyone. So this will become important further on. Okay, so an app model bills for the life cycle of an instance. It handles concurrent requests and accommodates for compute time outside of the scope of a request. A function bills for the lifetime of a request, handles a single concurrent request, and assumes this sort of freeze-thaw model in between requests where no CPU activity is going to be allowed to happen. Okay, eviction. So we talked about request comes in, we don't have an instance available, so we're going to create an instance for you. And then you have a trough in your traffic, and we have 1,000 instances lying around. What policy do we use to evict these instances, to remove them from our infrastructure? Okay, that's just showing what an eviction is. So generally, instance eviction is lazy, meaning that we will tend towards evicting instances when we need the infrastructure that they are consuming, but not before. The reason for that is that the machines on the data center floor largely have a fixed cost, whether your process is running there or not. There's an opportunity cost to us if you have a process that's running and we need that space for somebody else and you're not using that space, in which case we'll kick you out. Generally though, what we try to optimize for is not whether we are creating or destroying instances. That's much more of an implementation detail. We just try to optimize for performance. We monitor things like latency. We monitor things like cold starts because they're bad for performance. And we try to optimize the scheduling algorithms or try to alter the scheduling algorithms to optimize for those two things. As a side effect of the concurrency that I described before, apps will tend to have cold starts less frequently. And that's because when each subsequent request comes in, it can be dealt with on the same instance. And the time between, the number of instances we have to create to serve the same QPS is fewer. And then the last point is, sometimes instances just go bad. Maybe you hit an out-of-memory error, and even though that request that caused the out-of-memory error is long gone, the machine has found itself or the instance has found itself in a bad state. We'll detect that and we'll cease to send traffic to them. Because we're ceasing to send traffic to them, they will become viable for eviction at some later point. Okay, quick recap. Serverless is awesome. It's also not awesome when you can't know what's going on. Google knows how to serverless. You all do too now. So I expect to see many serverless compute competitors emerging after this presentation. And then we talked about the life cycle. What happens at deployment? We talked about atomicity of deployment, instance creation, destruction, cold starts, apps versus functions. Background threads we didn't talk about specifically, but this was the compute time in between the request. Okay, but what do I do with all of this amazing information that I've just been told? Okay. There's some sort of patterns and anti-patterns that I want to talk about. So let's look at some common pitfalls that people fall into. Number one, are we choosing the right primitive? Are we trying to jam an entire Java Spring application into a function? And is that the right thing to do? What can we do to improve our cold start time? What are the best practices there? Oops, I'm sorry. What do we do with background threads? I have this thread that's running in the background. Common pattern in web applications is receive the request, respond quickly, and do some work in the background. Well, that's not going to work in a function, because once you've sent the response back, that's a signal to us that you're done, and we're going to throttle the CPU down, and your background task may or may not complete. What do you do with this auto-scaling, where we scale out beautifully, and you denial of service your own database because it can't deal with the traffic that we've been sending it because we auto-scaled? And then I'll talk a little bit about idempotency towards the end. Okay, number one, choose the right primitive. Do you want to put your big Java monolith into a cloud function? Probably not. You can. You're going to have horrendous cold start times, and they're going to happen very frequently, and everyone has a bad time. Do I put my big Java monolith into App Engine? Maybe. Why wouldn't I? Well, I wouldn't if I'm relying a lot on state. Serverless compute products work best when they assume that they're stateless. If you have to persist state, you will find circumstances where the request where you assumed that state was there finds that it's not there. Now, it's a great performance optimization that you might be caching things, and if it's there, it works faster, and if it's not, you can go get it, and that's fine, but this is why I say maybe. The best thing to do is to make sure that the application has the appropriate granularity of services. Very, very tiny services, cloud functions, medium-sized services, App Engine. Some anti-patterns with relation to cold starts. Again, if you assume a stateful environment, then this might be problematic. What I mean by that is that in a classic monolithic web app, it's very common for the start to load a bunch of state. Maybe it's loading things from a database into cache. Maybe it's instantiating objects ahead of time, instantiating singletons, whatever the case may be. This design pattern assumes essentially the virtual machine style mode of operating, where you start up the VM, it does a bunch of work. It might take 5 minutes to start, but that's okay because you're only doing it like once a month. This doesn't translate well to serverless because this start-stop cadence is much more frequent. And then the last point there is this primitive choice. Choose the right primitive. Now, Google need to do the right job in making that easy for you, but really choosing the right primitive sets you off on the right foot from the beginning. Okay, here's some code, in case you didn't notice. If there's any Node.js developers in the audience, don't come and attack me afterwards, because what I'm going to show you is pretty much the antithesis of what a Node.js developer will tell you is best practice. And they'd be right, but I'm going to show it to you anyway, because I think it's a good illustration. This would be pretty common in a Node application, and I'll just unpack what's happening here. I have some libraries, some dependencies. They are being required at the top of my file, the first thing that happens. And then I have two functions declared in the same JavaScript file. I have do something and do something else. Each function uses only one of those dependencies. And I said, this would be a totally sane pattern in an application model or on a virtual machine. The first function uses the first dependency, the second function uses the second dependency, everyone's happy. But the problem is, the second function doesn't use the first dependency. So if I was deploying these as separate cloud functions, even though they were in the same source file, the do something else would be its own function. But at cold start time, it would be loading the first library, even though it never ever uses it. Now, multiply this by 10. How do you know that all of the things that you're doing at the start, and I'm doing something pretty innocent here. All I'm doing is following Node best practice. I'm just requiring a bunch. I'm not loading a cache. I'm not doing anything silly. I followed what they told me. But the side effect of this is that each function, when deployed individually, is bearing the cost of all the other functions. So this is unwanted cold start time. It doesn't offer me anything. It just costs me money. It's a more insidious example. The function is using both libraries, but only conditionally. So if my query string foo only equals bar in 1 out of 1,000,000 requests, then all the other requests are paying the price for that in terms of cold start time. This takes a little bit of relearning in how we do things. We have to be mindful of what's going to happen at startup when I deploy this thing. We often hear, oh, such and such product or such and such platform has good or bad cold start times. But largely it's dependent on this code that we write. Okay, this is where I'm going to get in big trouble. I'm not saying necessarily do this, but this would help. I only require the library when it's actually required. Now, a really great feature of Node is that that require statement will be cached. And so the subsequent invocation of that on a hot instance, it's effectively a no-op. But this is, again, just illustrative. The else condition that happens in most cases, let's say, doesn't pay the cost of some huge lib that's loaded in the if condition. Hope that makes sense. Okay, I want to invite my colleague Monica on stage. She's going to give you a demo. Can we switch to demo, please?
Thank you, Jason. So my name is Monika Nawrot. I'm software engineer in Cloud Functions team. And for the purpose of this talk, I created a demo that illustrates what Jason has just said. So it elaborates on cold start and life cycle of Cloud Function. So in my demo, I created the functions, or rather free functions that do more or less the same thing, but in a slightly different way. So I integrated functions with Slack. So Slack is a cloud-based tool that aids team collaboration. So I have my Slack channel, and I also created a free custom commands that are hooked with functions. So integration is very easy. As you can see, there's a command, and there's URL that should be called whenever this command is called, and it points to a function. So let's try a first function. So this function, well, all of these functions do the same thing, as I said before. So they expect a term in the Slack channel, and then they put this term in the knowledge graph API and retrieve information about this term from knowledge graph, and then returns a response which contains the data from the knowledge graph. So you can learn something about this particular thing from knowledge graph API. So the first function is written in application-like style. So as you can see, first, we extract the text, so the term that was written in the Slack channel. Then we use a local cache. So first, we try to retrieve information from the cache, and if it's not there, then we are making the actual query. The query is on here, so we just put the query to the knowledge graph API, and we extract the first result. And then we do the formatting. So we are converting the message returned from the API to the format that can be displayed on the Slack channel. So because it's application-like style function, I also do some preloading. So let's say that my Slack channel is about traveling, and people often look for information about the countries. So I want to make this experience for them really good, really fast. So I'm preloading some data associated with countries. So in another file, I have the list of all countries. So now let me go to my Slack channel and try this. Try to call the first function. And what actually happened is that Slack has quite aggressive timeout for the responses from the webhook for the commands. And because we are doing this preloading, we experienced the situation when actually the function was executed correctly, but just like didn't wait for the result. However, like any further call for the API should be extremely quick. So now let me go to the logs of this function just to see what exactly were the numbers. So how much did it take for a function to execute? So as you can see, the first invocation took more than 3 seconds just because we're preloading all the terms. However, any consecutive request was processed very quickly because we could serve the response directly from the cache. So now let's go to the second function, which would be written in a way that it's completely stateless. So this is kind of thing that you can expect when writing cloud functions. So again, I'm extracting text from the request. Then I'm not using a local cache as before. I'm just directly calling knowledge graph API each time I'm calling this function. I have also this this function that formats the query, and I do not do any preloading. So now let's go back to the channel and try the second function. So as you can see, I'm receiving the results reasonably quickly. Maybe try one more time. So in general, we can see it works. So let's again look at the exact numbers, how long this function was executed each time. So as you can see, like each time it takes a few hundred milliseconds to finish. However, the user experience is definitely better, but still the times are not perfect. So really the best approach would be the one presented in the third function. So you can go to the source. So again, we are extracting the query, but we also use a local cache. And so we are trying to retrieve the result from local cache if it's there. If it's not, we are querying a knowledge graph API. However, we don't use any preloading, so we optimize for cold start, but we still think that it makes sense to use a cache on best effort basis. So let's see how it works. So for different terms, it works similar to the previous function. However, for the terms that I'm executing for the second time, the function executes much quicker because they could be served from the cache. So let me see the logs. So as you can see, there's still a cold start that takes longer than consecutive invocation because this new instance needed to be created. However, any consecutive request for the same term can be very quick. So to summarize, like this demo shows two things. The first, that you should really optimize for cold start because they happen. They happen anytime traffic pattern changes and new function instance need to be created. And like as you can see in this example, this cold start time, if it's too long, may mean that your function is unavailable for the user. And the second thing, that platform is smart enough, so will not dispose your function instance just after it was executed, because it can anticipate that there will be some traffic. So it still makes sense to use a local cache to optimize the results. So this is all that I prepared, so we can switch back to the presentation.
Thanks, Monica. Yeah, so what we just saw there was a much better version of what I had put on screen, actually done by a real engineer. Okay, so just to summarize. It's important to understand and optimize for cold starts. They happen when a new instance is created. We will create new instances when they're needed. And then because functions only serve a single concurrent request because billing, that happens even more frequently in the functions case. Again, this period of time in between requests in the function case, and what do you do with that with background threads or background tasks that you might be running? As I said, it's very common in the sort of web application world that you might want to early respond to a request and then do some work, some more heavy lifting in the background. This is not going to work very well in a function abstraction because of this CPU throttling behavior. The best practice here is, if possible, wait for all the work to complete before you return. If you want to give the user or the caller a response early, then you should. We would recommend that you use some sort of event bus like a pub sub, enqueue a message on that event bus, have some other function somewhere else that's going to do that background processing, and then return. And it's not just because of this CPU throttling behavior that we would say this. You can imagine the request comes in, I spawn a thread, I'm going to do some heavy lifting over here, but I'm responding immediately, and then I get halfway through the heavy lifting and the thing crashes for whatever reason, out of memory, process dies. What happened to that work? What are the guarantees that I'm providing myself over that work? Probably much better is to have an at least once guarantee on an event bus like PubSub, so that if it does fail, it will retry and eventually succeed. Special call out to connection pools. Somewhat unsolved problem. Traditional database, MySQL, Postgres, take your pick, will have a finite number of connections it can deal with on a particular instance or in aggregate. You have a spike in traffic. It overwhelms the database, too many connections. And this is displayed here in my nice graphic. There's a couple of things you can do here. There isn't really a silver bullet for this because it's a fundamental mismatch. There's a fundamental sort of impedance mismatch between a finitely scaled resource and I hesitate to say infinitely, but much larger scaled compute layer above that. A couple of things you can do. Data access service pattern and scaling controls. I think I repeat myself there. So limit exposure to the database to only the services that need it. Don't just throw your connection pool into every single function you do. Be diligent and judicious about who is accessing the database. Another idea is to break your database up itself. Sometimes difficult if you're relying on foreign keys and things like that, but as a pattern, it can be useful. Limit connection pools, the connection pool size. And we have this sort of somewhat strange recommendation that we make in Cloud Functions where you create a connection pool to a database like MySQL and you limit it to a size of 1. Why do I need a pool if it's a pool of 1? Why don't I just make a connection? Well, it's limited to 1 because first of all, you're only dealing with a single concurrent request, so the likelihood of you ever needing more than 1 is pretty low. And secondly, if you just left it default, and let's say the connection pool framework you're using says, I'm going to create 10 connections by default. Every single instance of that function is going to create 10 database connections. You're going to run out of connections pretty quickly. The reason we say to use a connection pool is really just a convenience because many connection pool frameworks will do things like re-establish the connection if it's found to be bad. And so you just get greater reliability by leveraging that kind of retry behavior that's native to the connection pool. Another thing you can do is use rate limits at an API level or scaling limits at the infrastructure level. For those who saw the presentation yesterday, we talked about a new feature in Cloud Functions that's coming soon, which allows you to limit the amount that we scale up. So you can have some levers there to say, please don't DDoS my database. I can only deal with 100 connections. I know I have 1 connection per instance. I know I have 100 instances maximum. Or use a quote-unquote serverless database, like Cloud Data Store, where we handle that scaling for you. Okay, last point, idempotency. I have a quote there, which is sort of often attributed to Einstein. I'm not sure if he actually said it. Doing the same thing over and over again and expecting different results. Was he talking about idempotency? I'm not sure. So idempotency is when I perform some operation, and no matter how many times I perform that operation, the outcome doesn't change. It changes the first time and then doesn't change thereafter. So this is really important because in many circumstances, particularly in asynchronous event-based functions, the guarantees are at least once. At least once means we'll execute you at least once, but not exactly once. And there are circumstances where you will you'll be executed more than once. You know, I have a reference to something like an upsert there, where you can mutate the data, but if you do it again, nothing changes. This is a concrete example. This is actually my inbox from about 2 or 3 weeks ago. I don't know if this was an idempotency thing, but it seems like it might have been. I received, and actually it was more than 19. I took the screenshot too prematurely. But you can imagine this situation where you have a bit of code and it's sending an email. But it's sending an email and then it's doing something else. And the something else fails. And they have a retry policy. And so it's sending the email and then failing, and then sending the email and failing. So it is not idempotent. So a failure that leads to a retry is correct behavior. You want this thing to happen. But a failure that causes mutations or sends SMS messages or whatever it might be and then fails is definitionally not idempotent. So there's many ways to solve for this. We're not going to dig deep on that now. Just something to be mindful of, particularly in serverless, particularly in asynchronous, where at least once guarantees are the norm.